Okay, so we'll start. All right, again, the first midterm is going to be the coming Thursday, and Dr. Eldridge and myself will be sending out emails about more details, but it will cover all the material from lecture 1 to today's lecture, okay? So the next Tuesday's lecture will not be covering the first midterm. Okay? And I would also add an extra office hour on Wednesday to help in case students have questions. All right, so um, okay, so so far we've seen sorting last time, and before that, we saw that if an array sorted, then we can answer queries such as a search query or maxima minima efficiently using a sorted array. Okay, now imagine that you are maintaining a database indexed by some key, say numbers, real numbers. Okay, and let's say that you want to support operations, which includes not only just a search operation, um, finding maximum, minimum, or finding the so-called successor and predecessor, which means that the number following a certain number, okay? And let's say that you're also interested in the so-called dynamic operations, which are the following, okay? This, you may want to insert a new key, a new record into your database. You may want to delete an existing one, or you may want to find the one which has the maximum key value and remove it, delete it, and so on. Okay, so these operations are called dynamic operations because they're going to change your database. Okay, while operations like what we've seen before, like a search, if you're searching for a specific element, that's a static operation because it does nothing to your database. Okay, your database remains intact. Okay, so let's say that now, because I mean, in general, that's what happens with real database. We may want to change it. We might want to update it. Okay, so we want to have operations which are not only the static one that we've seen before, okay, but also the new dynamic ones. Okay, let's see how we can support such operations. All right. Now, we already mentioned before that if I sort these keys into a sorted array, then we can use binary search to perform the search operation. And that binary search takes time log n, where n is the size of your current database. Okay? And once your array is sorted, finding the largest key is very easy. I just go to the last element, so that's constant time. Same for minimum. And if you already know which element you're looking for, finding the one following that, the successor, the one whose order is just after that, is also just go to the next entry. So it's also constant, same as a predecessor, finding the number that's before it. Okay, so all of this are quite efficient, which is great. Okay, so once you perform the pre-processing to sort the array. Okay. However, think that suppose you want to now insert a new element. Okay, now you also want to make sure that after insertion, you want to keep that array still to be sorted because that's in the future. So that in future, you can still perform, say, search and all this operation efficiently. Okay, what do you do? Okay, of course, you can say, I can just use dynamic array and add it to the end, but then the new array may not be sorted. You have to resort it. Okay, and deletion is even harder because now you have to remove an element and you have to shrink your array. Okay, so this approach we've seen before, sorting the input elements in the array and then perform binary search-like operation is not good for dynamic updates. Okay, so what we want, in fact, you can using a sorted array, you would have to spend linear time for each of this dynamic operation. Okay, so the idea is that can we actually organize the data in a better data structure, okay, so that we can support all of these operations, not just the static ones, but also these dynamic ones efficiently. Okay, so that's what we want to do today. Okay, so today the data structure we're going to introduce to achieve this is so-called a binary search tree. And some of you may have already seen this in the DSC40. Okay, so we'll see that this can easily support all the operations from the previous slide. Okay, and the time it takes is proportional to the height of the tree. Okay, we can further make this binary search tree to be a balanced binary search tree, which makes sure that the height of the tree is as small as possible in some asymptotically. Okay, and in the end, I'm also going to show you, once we have the binary search tree, how can I also use this to do select query that we discussed the last time. Okay, all right. So first, what is the binary search tree? Okay, some of you, as I said, may have seen this before, but let me just review the concepts here. Okay. Well, first, what is a binary tree? A binary tree is just a rooted tree where every node has at most 2 children. Okay, so for example, here the node 3 has 2 children, 2 and 4. Okay, and to implement that, you can just represent using a linked data structure where each node will contain the following fields, which contain the key value, which will be like 3 is the key of this node, and will contain a left pointer. So for this node X, the left pointer will be pointing to the left child, and the right pointer would point to the right child, okay? And in general, a node would also return a parent pointer to point to its parent, okay? So, so in this case, the parent of 2 is 3, the parent of 4 is 3 as well, okay? So in the binary tree, the root doesn't have a parent, but for all others, you have the tree like this. Every node has a parent other than the root itself, okay? All right. Now, so for example, with this information, with this data structure, or the left and right pointer we store, if we start from the root of this example, the tree in this example, and if I keep following the left pointer, that means that from this one, by left pointer, I'll go to its left child, I go to the node containing key 6, and then following the left pointer again, I go to the key containing 3, and then the node, and then following left pointer again, I would go to the node containing 2, and then the 2 is a leaf node, which means that both of its left and right children are empty, so we use nil, or sometimes you can use null. Okay, depends on whatever programming language you're using. Okay, but it's basically a null pointer. Okay, so by following this pointers, we can move around in the tree. Okay, another example, if we're at 17 and we follow the parent pointer, so the parent, so now we follow the parent pointer. So the parent of 17 is going to give us 18, and then the parent pointer of 18 give us 13. And then 13 is the root. It doesn't have a parent anymore. So we say, okay, this process terminates. Okay. All right. So these are all quite standard. And as we said, the binary tree is a rooted tree where each node has at most 2 children. And a node is the root, only one node that's the root of the tree. If its parent is nil, okay, so only one node can have the parent to be nil, again, my use of nil is the same as the null pointer, okay? So, and a node is a leaf if both of its children are nil, okay, which, for example, these are all the leaf nodes because both of their children are empty, okay? And in general, we talk about the left subtree or right subtree. For example, if we consider the node X as the root, the left subtree of this is basically the subtree rooted at its left child. So this subtree is the left subtree of, this is the left subtree of X, okay? The right subtree of X of this root is basically the subtree rooted at its right child, okay? So this is the terminology we're going to use. All right, and a complete binary tree is basically a binary tree where every node other than the children, other than the leaves, have 2 children, okay? So this example, this is a complete binary tree because every node other than the leaf node, they have exactly 2 children, okay? So what is an incomplete tree? This tree will not be a complete. So this is not a complete binary tree. Some of the nodes has only, I can even do this. So some of the nodes has only 1 children, okay? All right. Okay, in fact, it's a binary tree where all the nodes have 2 children other than leaf. And okay, so now those are the just standard binary tree. Okay, so what is a binary search tree? Okay, a binary search tree is basically a binary tree with some special property regarding the key value it stores. Okay, what are the special property? The property is that for every node x in the tree, the value stored in the left child is smaller than the value stored at x, while the value stored in the right child is bigger than the value stored at x. Okay, so sometimes I just say that this is basic says the number stored at x is bigger than the one stored at its left child and smaller than the one stored at its right child. Okay, and a tree, binary tree T will be a binary search tree, which I often use BST to represent if it satisfies this property for if all of the nodes satisfy this property. Okay, and it's not hard to convince yourself that even though that this property just says that for every node, only compare the value at the node with its left, the left child and the right child. But it's actually easy to convince yourself that as a consequence, in a binary search tree, for every node x, so you have a node x here, and remember this is right child, and the right child has a subtree. This is a right subtree, this is left subtree. It's easy to show that everyone stored in the left subtree will be smaller or equal to the value stored at x, while everybody stored in the right subtree will be bigger than or equal to the value stored at x. Okay, so this is important fact of the binary search tree. Okay, so let's look at an example here. So this is a valid binary search tree. So for example, consider the root 13. Everyone, clearly 6 is smaller than 13, but 18 is bigger. And in fact, everyone in the left subtree, all the numbers stored here are smaller than 13, while everyone stored in the right subtree, they're bigger than 13. Okay, and you can verify this holds for every node. For example, same for 6. 6 is bigger than everybody in the left, while 6 is smaller than everybody in the right. Okay, so this binary search property holds for every node. Okay, all right. So here is a tree which is not a valid binary search tree. Why? Can you see why? Well, we see that for the node 18, okay, its left child is actually bigger than 18, while the binary search says that search property says that everyone to the left should be smaller. So here, this is a violation of the binary search property, okay? 19 is bigger than 18, so 19 cannot be in the subtree, left subtree of 18. So 19 has to be the right subtree. Okay, so this is not a valid binary search tree. All right. Okay, so so here are some properties of a binary search tree. Number one is that if we're given the same set of numbers, there are many possible binary search tree over them. So for example, this is one valid binary search tree over this number 2, 3, 4, 6, 7, 8. Okay, so what I show here is one valid binary search tree for that. But I could have another one. So here's another simple example. I could have 8 goes to 7, go to 6, 4, 3, 2. It's not a very pleasant looking tree, it's just a path. Okay, everyone has exactly one child, okay? But still, you see this satisfies the binary search property because every node, the number stored in its left child is always smaller than this node itself, okay? And the same for the right, but since the right one is empty, so that's also holds, okay? So both of this are valid binary search tree for the same set of numbers. So binary search tree is not unique. You can have many, many choices. Okay, in fact, you can enumerate how many possible choices that one may have. Okay, all right. So that's one property. Second is that if I give you a binary search tree, where can I find the minimum of all the key value? Okay. So if you're watching this offline, you can take a moment to think about it. But so here's the idea, right? So I want to find the minimum. I started at the root, And I know that the minimum has to be the smallest. That means that the minimum can only be in, if I have left child, then the minimum can only go to my left subtree, which means that I should follow the left pointer. So here I still have left child. That means that the minimum can even be smaller. I have to keep going left because the left is always smaller. Till when I'm at this node, I don't have a left child anymore. Okay, that means that I found the smallest possible. Okay, so in this case, the minimum is 2. Okay, the same idea holds for maximum. Now, one question is that, does the minimum have to be a leaf node? Okay, remember a leaf node is one that doesn't have any children. Okay, so does it mean in this case the minimum 2 is a leaf node? But is this true in general? Okay, you can think about it. And the answer is not necessarily so. So for example, if I put this one here, have another right child, which is say the value I'm storing is 2.5. You see, this is still a valid binary search tree, okay? And it's the minimum is still 2 because I just keep following left pointer till I cannot, okay, to the smallest one, but it's not a leaf node anymore, okay? So the minimum doesn't have to be leaf, but we know for sure it cannot have left child because it has a left child, that means there's someone who is smaller, okay? All right. Yeah, so this is in fact an example where in this example, minimum is 3, which is not a leaf. Okay, so now you are given a list of a tree containing n nodes, so storing n numbers, okay? As we said, the binary search tree is not unique. I can have many choices, okay? What is the tallest possible binary search tree? What is the height of the tallest possible binary search tree? In other words, I want to make it still to be a valid binary search tree, but then the height is as large as possible, okay? So what do you think? Well, in the example we've seen, basically, if everyone has only one child, then essentially you get a pass, right? So like the one we just saw, you go from large to small, you arrange it so that everyone has only one child. So when you have a pass, a tree of either this form or a tree of this form, okay? So if a binary tree has this shape, then its height is large as possible. The height is in fact m, okay? So that's the tallest one. The other question is, what is the smallest possible height for a binary search tree? Okay, now here we have a constraint because every node can only have at most 2 children. Okay, so if I don't have this condition, I could have a node where I have n-1 children. Then I have a tree of height only 2. But that's not possible in a binary tree. We have a binary tree here, everyone can only have at most 2 children. Okay, so what is the shortest possible height of a binary search tree? Well, if you think about it, basically I want to make the tree as fat as possible. Okay, that means that everyone will try to use both children. So everyone has exactly 2 children. And till I finish plotting all the numbers, okay? So, so this would be a complete binary tree. And if you have total number n, a complete binary tree has height log n. In fact, it's log base n, log n base 2, the ceiling of that, but asymptotically, this is simply log n, okay? So let's in fact see why in the complete binary tree, I have log height. Well, because that if the height is h, okay, how many nodes do I have? Well, what I have is that the first level, I have 1 node. The second level, I have 2 nodes. The third level, I have 2 squared because everyone has exactly 2 children. So in other words, in the hth level for height h, in the last level, I have 2 to the h number of nodes. So altogether, this is basically this number of nodes, okay? So if I want this to be n, then that when you solve this, you have that h basically equal to log n base 2 minus 1. Okay, this is without the ceiling. Right. Okay, so this is just a big theta of log n. So the highest possible height of the tree is the nearest height. The lowest one is asymptotically log n. Okay. Now this is good to remember because for a binary search tree, that means that there's a range of its height. We cannot go above n. We cannot go below asymptotically log n. Okay. All right. Okay. So let me